When I started Okay, hey, welcome everybody. I'm pretty excited to have Claire Richardson with us remotely today. She's dialing in from Tempe, Arizona. She's a PhD candidate at ASU, working with Ed Garnero on deep seismology. So she's going to talk a lot about that. She's an NSF fellow, graduate fellow at the moment. She's also a member of the board of the Inclusive Community Committee at ASU's School of Earth and Space Exploration. That's it's an environment, learning environment, equity committee. And let's see, in the past, she's been a recipient of outstanding undergraduate and also 2 Seismological Society of America community grants. And 1 ASU College of Liberal Arts and Sciences graduate completion fellowship. And I promised an anecdote. So so she recently published, with her advisor, an article in Physics Today. So she got a call from me. But I'm looking at these blobs that she's going to talk about, and I looked at them in relation to the continents, and I thought, wait a minute. These are, they're asymmetrical. I wonder if they are related to the South Atlantic anomaly. And raise your hand if you are familiar with the SAA, South Atlantic anomaly. That's a 0. Interesting. Oh, Sukant knows about it. Excellent. Thank you, Sukant. Wow. Excellent. The South Atlantic anomaly is a irregularity in the Earth's magnetic field. It's as if, so if you were to replace the Earth's magnetic field with a bar magnet, the bar magnet would have to be displaced to the north and also kind of towards Singapore, something like that. But it's more complicated than that because it's not symmetrical. But it's a danger to satellites, and satellites have been lost by not duly considering the South Atlantic anomaly, because the particle concentration from the solar wind is different there, and you get wild fluctuations in radiation levels. For instance, there was a Japanese satellite, an X-ray telescope, that was lost because it passed through the SAA. It scrambled their direction finder for a brief time, but that brief time was important because they needed to burn. They needed to have a thrusting event. And they thrust in the wrong direction, and they ended up losing their whole satellite. Anyway, I looked on Wikipedia. So the end of this is, I looked on Wikipedia to see if my intuition was even anywhere correct. And it turns out, yeah, Wikipedia says the SAA is probably due to your topic today. So that's your lengthy and anecdotal introduction, but thank you for coming in. We'll shut up and listen now, but welcome.
Cool. Well, I'm really excited to be here. So thanks, Guy, for that introduction and for inviting me. This is really kind of a full circle moment for me. It's pretty exciting. So today I'm going to be talking about this Physics Today article that Guy mentioned, that Ed and I published last month. And it's titled "The Mysterious Massive Structures in Earth's Deep Mantle," which is kind of a flashy, Physics Today title for just these 2 anomalies that we see on the core mantle boundary. So that's what I'm going to be talking about today. And I also want to say, so I'm at ASU. I'm just shy of 4 weeks away from the end of my PhD. So getting very close to just being PhD instead of PhD candidate. So with that, I'm going to dive into some just some kind of broad brushstrokes background material. So I work on the Earth. And I know that this is a physics and astronomy department. So I wanted to just kind of give some background on the types of physics that we use for looking at the Earth. So we differentiate the Earth into different spheres. So you have the atmosphere, the cryosphere, the critical zone, And then there is like just the solid earth. So when I say that, I literally mean the parts of the earth that are rocky or metal. And so to investigate the solid earth, we apply different physics principles. So in the deep earth interior on the global scale, there are kind of three main things that we care about. The first thing is mantle convection. So the mantle is solid rock, but there's a huge temperature and pressure gradient between the surface and the core mantle boundary and the center of the earth as well. But in the mantle, that gradient over geologic timescales, so over millions of years, hundreds of millions of years, the mantle actually deforms plastically. And so we can use fluid dynamics to model those convective patterns. And at the surface, you can actually observe that. So we know that there are tectonic plates and that they move around and make earthquakes. And so tectonic plates actually move at about the rate that your fingernails grow. So that's the like real-time rate of convection, or a proxy for that. So we use fluid dynamics for simulating mantle convection. We also care about the composition of rocks and minerals in the deep mantle, and that's basically just material science. So at temperature and pressure conditions deep within the earth, we can, in a lab, we can synthesize these materials and understand their properties. And then to look at the actual physical structure of the earth, we use seismology, which is basically just wave physics. And so together, these make up this kind of multidisciplinary umbrella field of SETI, which is the study of Earth's deep interior. For those of you who are in astrophysics or astronomy, it's not, the SETI that I care about is not extraterrestrial intelligence. It's Earth's deep interior. So just to be clear about that. And so I'm going to be talking about all three of these today, but mostly I will be focusing on what I do, which is the seismology component of this, so the physical structure. Okay, so how do we actually image physical structure in Earth's interior? Well, you can imagine when an earthquake ruptures, it sends energy out that propagates throughout the entire interior of the planet. And so this is just a simulation showing the global wave field of potentially from some event and what that looks like in the interior of the Earth. So these waves sample this material and they are recorded at seismometers on the surface. So all of this energy is rippling through the Earth and it's recorded as seismograms at the surface. And this is showing S waves in blue and P waves in orange. And so those are the two fundamental types of waves that we care about in seismology. So P waves, in the deep earth, I should say. So P waves propagate, they're compressional waves, they propagate in the radial direction. So it's kind of like a slinky. If you were to push and pull the end of a slinky, you would get propagation forwards radially along the in the radial direction. And then we have S waves, which are shear waves. And so shear waves propagate in and out of the plane relative to the direction of propagation. And I'm going to be mostly talking about S waves today. So I just want to be really clear from the get-go, because that's something that I can kind of glaze over. So a lot of the stuff that I mentioned today will be regarding S waves, because they're a little bit more robust in terms of their sensitivity to structure in the deep mantle. And then, yeah, so another kind of convention that we use is when we're representing waves in cross-section. Generally, we will just use the 1D ray path to show different types of waves because you saw that simulation of all the different waves, it gets quite complicated. And so if you see a diagram that looks like this, it's just representing the 1D ray path for the perpendicular propagation along that wave front. So here I'm showing an example of a direct S wave, which just travels directly between the source and the receiver, and then an SCS wave, which is a wave that bounces once off of the core mantle boundary. And so this is an example of what that would look like in the data when it's recorded at a station. So you have the S wave arriving first. It has a slightly higher amplitude because it's been attenuated less because it hasn't traveled through quite as much material. And then a little later on, you see the SCS wave appear. It's a little bit lower amplitude, but it's still a nice arrival on this seismogram. And so when we look at the global wave field for, this is an example of an earthquake in Fiji, and it's recorded at all of these different pink stations, you get something that looks like this. And this is kind of horrible to look at, but basically what I'm showing you is, so distance is here, distance from the event is on the y-axis. So we're getting farther away from the earthquake as we go down this plot. And then time is on the x-axis. And so each of the lines on this plot is a seismogram. Each line is a seismogram. And each little wiggle represents an interaction with a different interface or a different, a diffraction or reflection, some type of energy that's being produced from this event as it propagates throughout the interior of the Earth. And the most important thing is that there are you can see global patterns. Like if you didn't know anything about this plot and what I'm telling you right now, you could look at this and say, there's a little bit of noise, down here, but for the most part, there are really recognizable patterns in these data. And so this is a collection of about 5,000 seismograms. This is an earthquake that happened in 2018. But I'm going to ask you for a second to step back in time a little bit. And say, it's 100 years ago, we're sitting in an office, we have like a handful of measurements from global seismometers, and we have we know that the Earth is round and it's rocky. And so that gives us an idea, a very broad idea of when earthquakes, when certain waves should arrive at different stations around the globe. And from that, we can make some predictions. So this is work seminal work by this person, Beno Gutenberg, who had this model that's represented here. His predictions would have been along this black dashed line, but his measurements actually predicted something that looked more like this red line. And what this eventually fell out to is he used these data, these observations, to make a model to explain those data. And what that eventually gave ended up showing is this really drastic difference between wave speeds for both P and S. And it shows this distinct difference between the properties of the mantle and the core. So this is essentially the discovery of the core-mantle boundary, where you have the silicate, the rocky mantle coming into contact with the liquid iron or the liquid metal outer core. And that's represented by this really sharp change in physical properties. And so that kind of observation, that kind of research ultimately yielded this kind of layer cake view of the Earth. So you have this person, Andrija Mohorovičić, who discovered the boundary between the crust and the mantle. Gutenberg found the boundary between the mantle and the outer core. And then a woman named Inge Lehmann found the boundary between the outer core and the inner core. And this was all done, in the first part of the 20th century. And this layer cake model kind of remained the prevailing view for a few decades, probably more than that, actually. But around the same time that these discoveries were first happening, maybe even a little bit earlier in like the 1910, 1915 kind of time frame, there was the proposal by this person, Alfred Wegener, that continents actually drift around on the crust. that at the time was kind of dismissed as like pseudoscience. But, you know, he had these lines of evidence like Africa and South America. It seems like they kind of fit together. Geologically, the same rock units are present in England as they are in New England. So, you know, there's a big ocean between those, obviously. So he kind of had this idea that, like, at one point, these continents, these land masses were probably stuck together, and then they moved apart from each other. But there wasn't a sustainable kind of dynamic framework to support that. And so it just kind of didn't catch on. So we have this layer cake model that doesn't have any lateral heterogeneity in it. And this is interesting because it kind of goes to this. I'm going to talk about the magnetic field a little bit and how it's modulated by these mysterious structures. But the kind of the smoking gun for plate tectonics and the revival of this continental drift theory was actually the discovery of magnetic lineations on the seafloor, which showed that mirrored along a ridge, on a linear ridge on the seafloor, it seemed like there were these magnetic reversals. So where, you know, we have a magnetic field. And it kind of was like where the dipoles switch. And so that was discovered actually because of some magnetic, it's like U-boat surveys in the Second World War. And that kind of showed that the plates are actually moving apart from each other. So there's all of a sudden this mechanism, this proof that continental drift is happening. And that kind of changed everything because people had to start thinking about a dynamic planet. And if we conserve mass, new stuff that's created at ridges in the ocean has to go somewhere. So it has to basically fall into the mantle with, you know, through plate tectonics and subduction. And so, you know, plate tectonics was developed and the idea, a supported idea for lateral heterogeneity in the mantle kind of started to emerge because there's, you know, more and more seismic instruments that are being deployed and more seismic proof for lateral changes. And so the community kind of got together and decided we need a model, we need a benchmark model of the average Earth so that we can start to define things that do not look like the average Earth. And so in 1981, this model, PREM, the Preliminary Reference Earth Model, was developed. And it's a spherically symmetric 1D model of the average Earth in terms of elastic properties. So you have S-wave velocity in blue, P-wave velocity in orange, and density in green. And in this model, the core mantle boundary is close to 3,000 kilometers deep, and it's has this huge change in physical properties when you pass from the rocky mantle to the liquid outer core. And then there's another really significant change at the inner core boundary, where you go again from liquid iron, basically iron nickel alloy, to the solid metal inner core. And then the center of the Earth is at, in this model, is 6,371 kilometers. So this was, the development of PREM was kind of it paved the way for modern seismology and for the discovery and quantification of seismic anomalies. And so throughout this talk, when I say things like high or low velocity or perturbations or anomalies, I'm referring to things that look different from this model PREM. Okay, so now that PREM is developed, what do we do with it? So again, we have this just a regular S-wave. And so now we can use PREM to say, you know, PREM expects that this S-wave should arrive in a spherically symmetric Earth at about 1,000 seconds. And that's a convention. We use seconds in seismology, so I apologize for that. It doesn't really matter. But if you look at your seismogram, you can say, okay, I have an S-wave. This is 1,000 seconds. This is when my wave, quote unquote, should arrive if the Earth looks like PREM. However, if your observation is actually that the wave arrives, the pulse arrives for the S-wave at say 1,005 seconds, all of a sudden, you understand that something has had to slow that wave down by about 5 seconds. Something along that ray path has slowed down the arrival of the S wave by 5 seconds. And that gives us, that's what's called a travel time residual. And so if you have events that are scattered all around the Earth, if you have stations that are also scattered all around the Earth, you can get a really good dense sampling and actually map out exactly where these anomalies exist, where places where waves move slower or faster than expected. And that's the kind of the underpinning technique of a lot of modern seismology. It's a theory called tomography, and it's actually the same theory as used in CAT scans, or CT scans. So CT actually stands for computed tomography. So we're basically taking an ultrasound of the Earth when we do seismology. And so when we apply that method to using global data to the whole Earth, this is the model that we get for S waves near the core-mantle boundary. So this is showing this model. This is the most recent model that has come out. It's called GLAD M25. And this is kind of the image that we see. So here, the red colors are showing low velocities, and the blue colors are showing high velocities relative to Prem. And the reason that we use this color convention is because low velocity material is typically warmer, so hence the red, whereas cool velocity, cool rock will make waves travel faster. So that's this kind of anti-intuitive color scheme that we use, but that's what we're looking at. And so, of course, the two things that kind of jump out here are these two giant red anomalies. And when we look at them in 3D, this is kind of the view that we get. So they extend off of the core-mantle boundary, actually up to, over 1,000 kilometers. And they really kind of dominate the core-mantle boundary landscape. And so because these tend to slow wave speeds down, we refer to them very uncreatively and unfortunately as large low velocity provinces, so LLVPs. And I will be using that acronym a lot. But this is basically what they are. They're just big provinces of low velocities. And also I want to say on this slide, another convention in seismology is that we have not agreed on what the central longitude should be. So just beware that maps that I show are going to kind of vary in terms of the longitude that they're centered on. So anyway, so LLVPs were kind of discovered first in the 80s, and then we've since gotten better models. And just by their own existence, that creates so many questions about the nature of our planet. But specifically for LLVPs, questions I'm going to be addressing today are what actually defines them? What are they? What is their role in the dynamic Earth system? And how did they form? So I'll start with what defines LLVPs. So this is the first paper that actually showed, it's the first global model that was published. It's also by Adam Jawanski, who is the author of Prem as well. And this is the lowermost mantle. So he used P waves and you can for this model. And you can see kind of like a low velocity thing in the Pacific and kind of a low velocity thing underneath Africa, but it's not really these distinct two blobs. There's not a lot of, they're very diffuse. They don't have sharp margins. And so based on this model, the kind of first understanding is that they were thermal anomalies only. There's no different composition. And they're probably also dense. They used a little bit of gravity data in this model as well. And they're a little bit probably dense here. And so that kind of kickstarted this, this lineage or this subfield of global whole mantle tomography. And so here I'm just showing a progression of different models throughout time since then. So this is a model published in 1996, and then several others published in the last 15 years or so. And as these models have come out, our understanding of what these LLVPs are has kind of evolved as well. So there are questions of, are they intrinsically dense? Are they also chemically distinct? And, are they consolidated features, or are they just kind of like a collection, a forest of thermal plumes? It's kind of unclear, but what we have learned is that as the margins of these things have gotten more sharp, we've learned that that probably means that they have a chemical component to them. And they are probably somewhat consolidated, and they're probably intrinsically dense. At least the lower 100 kilometers of them are probably something is causing them to be intrinsically dense in terms of their composition. So we have learned a lot as time has gone by, and more models have been published. But you can see that these are still pretty different from each other. So there are still a lot of open questions that we have. And again, so here's this most recent model that I showed a little bit earlier. This is S wave speeds on the top and then P wave speeds down here. So this is just to show that we see it both in S and P waves. And then, as far as what defines LLVPs, loosely speaking, they kind of align with the lowest velocities that cover 30%, about 30% of the area of the lowermost mantle. But there are still, even this model looks different than those other ones on the last slide. So there's still a lot of open questions. And I'm going to talk a lot about that in the rest of this talk. But yeah, so basically because we don't have really great constraints on, really sharp constraints, I should say, on the small scale stuff in models of LLVPs, there are a lot of different interpretations that exist. So up here, I'm showing the example of if these are just thermal anomalies, it's a possibility that they are just kind of a forest of thin thermal plumes that are rising up off of the core mantle boundary. The whole thing might be positively buoyant and rising up into the mantle. It might be intrinsically dense and negatively buoyant. So it's hot, intrinsically dense stuff. With small kind of thermal plumes with maybe a little bit of chemical distinction coming off of the edges. And then it's also possible that there's kind of this battle between the thermal component and the chemical component that's causing kind of a metastability. So potentially they're very dense, but also very hot. And so the heat is making them want to rise into the cooler ambient mantle, but the density is keeping them anchored on the core mantle boundary. So the interpretation space is really big. And as far as what defines LLVPs, it's kind of unclear, but we have learned at least that they are these large antipodal anomalies that are really probably dense, probably very hot, and potentially probably chemically distinct as well. And they take up about 30%, of course, of the core mantle boundary. So that's kind of what defines them. And probably the more important question, or the question that most people want to know, is okay, they exist, but how do they interplay with dynamics? How do they interplay with mantle convection? And So I wanted to show this. This is from the article. And this is probably a much more accurate schematic of what's going on in the Earth. So it's not just a layer cake. There's a lot more, like it's a dynamically very active physical system. So you have the two LLVPs, you have these thin kind of thermal plumes that are upwelling off of them. You have tectonic plates that are sinking down into the mantle. They're very cold because they have been exposed to space, basically. So relative to the mantle, they're very cold. And as they downwell and subduct into the mantle, they drag material along with them. So they cause these big kind of downwelling currents. And then you also have these little things here that are referred to also, unfortunately, as ULVZs. So our acronyms kind of suck. But ULVZs are ultra low velocity zones. So whereas LLVPs kind of show like a few percent lower velocity than Prem, up to like probably 5%. ULVZs can be reduced up to like 50% in terms of S-wave velocity, which is huge. So those are also observed at the core mantle boundary. So really the interior of the Earth is this like richly dynamic space. And there are a lot of questions about how LLVPs interplay in this system. So this is the part of the talk now where I kind of go off the rails and start asking presenting a bunch of open questions. And so this part really kind of, it's the mysterious part of the title of the talk and of the article, which is code for we really don't know. So one of these questions that we have is, do they affect CMB topography? So if they're just thermal upwellings, it's possible that they kind of bow the CMB upwards within that flow pattern. As slabs subduct into the mantle and start to impinge on the CMB, those probably depress the boundary. And then again, either in the metastable or the fully negatively buoyant versions, they probably also depress the CMB. And this is obviously not obviously, it's not to scale. That's probably like maximum 10 kilometers of difference, which in something that's thousands of kilometers thick, it's there, but it's not super significant. But it does affect, say, patterns of outer core convection, which then affects the magnetic field and magnetic field reversals. And I'm going to come back to that. So another question we have is, do plumes form at LLVP edges? So those little thermal plumes that I've been referring to occasionally propagate all the way through, all the way through the mantle and actually penetrate through the crust and erupt on the surface. So that's what's happening, say, at Hawaii or Samoa. So if you think of volcanoes that kind of exist in the middle of nowhere, those are probably what we refer to as hotspot volcanoes that form from these whole mantle plumes. And there's evidence that they form, both geological and seismic evidence that they form at LLVP edges. And so this figure is showing, of course, the LLVPs in pink. And then the green dots are showing historical, what we call large igneous provinces, which we think are, there are these huge regions of lava flows. And so there's a big one that you're probably very familiar with, which is the Columbia River basalts. And then the stars are showing active hotspots today. And so it looks like the geology is also showing us that they probably come from the edges of LLVPs. And then a kind of sister question to that is, do ULVZs collect at LLVP edges? And the reason that this question is related to plumes is because ULVZs, they have this really dramatic velocity reduction. And it's very possible that you can only get that type of velocity reduction from some kind of melt component within these structures. And so there's kind of the question that exists that's potentially ULVZs are actually the roots of mantle plumes. So this map is showing, it came out in 2018, and it's showing kind of a global survey of all of the ULVZ studies, where the dark gray is showing studies that have definitely found ULVZs. The light gray is showing studies that have found that there are no ULVZs, and then green is where there's some complexity, let's say in the waveforms. So we're not really sure at the green places. But I think based on this map, the jury is still kind of out. With respect to whether they form around the edges of LLVPs, but they definitely occur. Some of them, at least, definitely occur at the base of plumes that we're aware of. So this is Hawaii, Samoa is down here, and then Iceland is up here as well. So there's probably somewhat of a correlation, but it's unclear if ULVZs are like uniquely mantle plume roots. Okay, so another open question is, are LLVPs the same? Are they the same height? Are they the same composition? Are they the same density? And the answer to that is also probably no. So this study was specifically looking at the heights of these two anomalies. And the important thing to take away from this is that the top of the Pacific LLVP, by the way, this is LLSVP, is large low shear velocity province. That's kind of antiquated now because we also see it in P waves. It's just LLVP. But anyway, so the top of the Pacific LLVP is at about 700 kilometers, while the top of the African LLVP is much, much higher than that. And there's some isotope evidence also that they may be chemically distinct from each other as well. So that kind of begs the question, why? And it's possible that there's some component of mantle flow that has to do with that. So we know that around the Pacific, there is what's called the ring of fire, and that's caused by, it's basically a big ring of subduction. So obviously up here, there's the Cascades plate that's subducting under North America. I'm sorry, the Juan de Fuca plate that's in the Cascade subduction zone that is subducting underneath North America. And then there's just all around the ring of fire, which is actually the cause for the ring of fire for all the volcanism we see, there's subduction. And so it's possible that because the Pacific is ringed by subduction and the African LLVP is not, there's some relationship with that. It's kind of unclear. And then I'm kind of getting close to the end of my open questions section here, but there's this question of how do LLVPs interplay with convection? So here I'm showing a geodynamic simulation of mantle convection. So the temperature field is this top panel, and the composition field is the bottom panel. And geodynamicists really like non-dimensional numbers. So composition can basically be understood as material that's intrinsically denser. The orange stuff is denser than the black stuff. This simulation actually came from a paper that was looking at how morphology changes in LLVPs modulate heat flux out of the core. And that does have a direct relationship with how the magnetic field behaves and how the pole kind of wanders. So I think that's probably the South American anomaly relationship. But anyway, so these are really important for like global processes and things that we see at the surface. And so answering these questions is really relevant. And then finally, there's also the question of, are they stable on the core mantle boundary? And potentially the answer to that is no. So there's a supercontinent cycle on Earth, which is basically like every 500 million years-ish, we get a supercontinent that forms. And so it's possible that when that happens, when there's a supercontinent, there's more of this LLVP material on one side, on the opposite side of the planet. So that's also a big open question. So to come back to this question, what is their role in the dynamic Earth system? I think, again, the answer is kind of still unclear, but they play a big role. And there are a lot of open questions. And so finally, how did they form? So there are a few possibilities for this. So it's possible that they're primordial reservoirs. So say this is your proto-Earth. Kind of the planet has just accreted. It's pretty well mixed, probably not this well mixed, but fairly well mixed. And then after a couple 100 million years or so, you start to get this process called differentiation happening, which is where heavy elements kind of rain out of the lighter, away from the lighter elements, and kind of go towards the core to start creating this iron core. And lighter elements like silicon and oxygen stay near the top. And so that's what kind of creates these minerals that are green. That's what I'm showing here. And then give it another billion years, and you end up getting this really nicely differentiated planet. So this is the rocky mantle, in this case, the liquid iron outer core, and the solid, I'm saying iron, what I really mean is iron nickel alloy, metal outer core and solid metal inner core. But if conditions are sufficient, actually what you can end up with is this thing called a basal magma ocean, that's made up of, it's like a dense magma ocean that kind of sits on the outer core like oil and water. And over time that cools, and these LLVPs form, whether that's through, mantle convection processes or what have you. So potentially they are reservoirs of like very early Earth materials. And there's also some isotopic evidence for this. Now, on the other hand, I would say it's not necessarily well accepted that Earth had a basal magma ocean. So the kind of opposing theory is that LLVPs are actually kind of piles of recycled crust. So here I'm showing a subducting plate. And when plates form, they have this kind of crust of really dense, like basalt. And then this light green stuff that's on this diagram is more kind of ambient mantle composition. And so as slabs subduct into the mantle, they thermally equilibrate, and the dense crust starts to delaminate from the mantle material, and that kind of accumulates on the core mantle boundary. And so then the last potential formation theory that I'm going to present here is they may be extraterrestrial. So about 4.5 billion years ago, when Earth was still very young, we think that it was impacted by this body that we call Theia. And in that impact, obviously there would have been a huge amount of energy and heat generated. And so that would have kind of liquefied, or both of these planetary bodies would have ended up being molten. And so this theory is suggesting that potentially there are some parts of Theia that are entrained within the deep Earth, and that those remnants have created the LLVPs. So I've just spent like probably 20 minutes telling you a lot of the open questions that we have. And so how do we actually go about answering these questions? A lot of what I posed, a lot of the scenarios that I posed are probably at play to some degree or another. But basically the answer is we need better models. We need better seismic models of the mantle to get away from this interpretation space and to get some real constraints from physics. So better models really start with better sampling. And this is a big issue in seismology. So this is the earthquake that I showed you earlier, of that big global wave field. So this is in Fiji, and it's recorded at these all of these pink stations. And you'll notice that they're all on land masses, and most of the landmass exists in the northern hemisphere. And so we have this big skew towards coverage in the northern hemisphere in terms of our sensors. And then with earthquakes, those also tend to occur along plate boundaries. So this is the Ring of Fire, and that's where we get a lot of earthquakes. And what this ends up looking like in terms of coverage of the core-mantle boundary is a pretty oversampled, relatively speaking, a pretty oversampled northern hemisphere relative to the southern hemisphere. And you'll notice this big gap around Africa, which is where we think one of these LLVPs is, where it looks like it is in the models. And so it's really critical to kind of improve this, to kind of fix this coverage problem. And I want to bring this image back up to say that most studies will use this wave. This is up here, it's the S wave, the direct S wave, and it turns into SCS. It's beautiful, it's high amplitude, it's really easy to measure. So it's really easy to use. And then potentially they will also use this wave here, which is the SS wave. So it's bounced once off of the surface before being recorded. And then also potentially this purple wave, which is the wave that has bounced twice off of the core-mantle boundary. So relative to all of the signal that exists on this image, that's not very much. And now I kind of cherry-picked this because it shows a lot of these other kind of what we refer to as backfield phases really clearly. So normally they're not used because they can be squirrely, they're kind of lower amplitude, they're harder to pull out of the signal, but they do exist, they are measurable. And they're just really underused. So there's a lot more information in the data that we do have that we can exploit before we say, start a bunch of campaigns to start deploying ocean bottom seismometers around the world, which is expensive and hard. So we kind of have the data already on disk. And this, you don't have to worry about any of the crazy names on this plot, but it's just to show that once we start actually incorporating a lot of these more quote unquote exotic phases, we can get a much better sampled mantle. And this is feasible because we're getting a lot more records per event these days, and so we can sample a lot more regions of the Earth. And then I just wanted to end the talk by saying, giving some proof that things are improving. So this is my part of my dissertation. I do mostly have done mostly method development to improve models. So this is an average of 4 of the models that I showed earlier, and this is their standard deviation. So this is just showing that like they are quite different from each other, especially on short-ish wavelengths. And so the method that I have worked on is trying to forward model what would happen if we try to map back travel time residuals into these models that they don't already explain. So that's kind of just a complicated way to say we're forcing these models to explain the data. So this is, again, 4 of those models that I showed. And when I apply this method that I've been working on, we see that they converge towards a single model, which is really exciting, and that they also mostly converge towards this one called GLAD M25. That's the one that they look most similar to, which is mostly accepted in the community as probably being the best model that exists in terms of methodology at this stage. So we're doing better. We're getting there. It's happening. So, eventually, hopefully we'll be able to answer some of these open questions. And so I just want to end now with some take-home messages. So things that I hope I have imparted to you today are, Earth is a really dynamic and heterogeneous planet. The core-mantle boundary landscape is dominated by these two LLVPs, plus a host of smaller structures. There are still a lot of open questions about LLVPs in terms of their physics. And we can improve seismic images by using more information from seismograms. And then if anybody is interested in reading the Physics Today article, here's a QR code for that. But that's all I have. So thank you so much for your time and for listening.
I just saw a note from Katie Cooper who says you had a great talk, Claire, and she's got to run to a meeting.
Yeah, sorry if that was a little bit long.
Just no, that's fine. Questions? Let me expand this window just a little bit.
Question.
Yes.
It's just, a naive question. Does gravitational field, surface field, ever play any role in say corroborating what you see from these earthquake signals?
Yes, definitely. So that's one of the, it's some of the other work that I've done previous to getting into the deep earth was on potential fields, and it's kind of difficult, of course, to parse in terms of depth where gravity signal is coming from. But there are studies that do, because we think about density a lot. So there are studies that actually invert jointly for density and seismic wave velocity. But then gravity, like global gravity surface observations, also kind of corroborate that there are these two really dense structures somewhere in the Earth. And so the seismology kind of places those at the core mantle boundary. But yes, definitely.
Sure.
Do any of its model assume Earth to be non-spherical?
Sorry, can you repeat that? I didn't have my volume up loud enough.
When calculating the distance that it takes for the earthquake to travel from one place to another, do you always assume the Earth to be spherical, or do you also break that assumption?
So no. In my models, there are separate models called ellipticity models, and so what we actually do is we calculate the effect of Earth ellipticity and then remove that from the seismic signal, because it's much easier to model a spherical body. But we do take into account Earth's ellipticity on the travel times.
I have a very quick, probably very random question, but in the LLPV community, is the mineral troilite talked about very much? FES is the.
I'm not sure because I stay as far away from minerals as I can. But it's kind of funny that you should ask, because my one of my good friends, most of his dissertation was on troilite, and so he spent a lot of time filing down meteorites to measure troilite spectra. But I'm not sure about its role, let's say, in the deep interior.
Yes, I didn't expect an answer, but I'm glad people still realize that troilite is interesting. There's yeah, Jeff.
Yeah, thanks, Claire. Interesting talk. Yeah, it seems like more and more of the data seem to confirm that the hotspots line up with the edges of the LLVPs. And do you have any ideas of why that is? Why don't you see it, see a big signal coming from the center of the LLVPs?
So it's a great question, and I would put that in the category of open questions because let's see if I can just zip back to this slide. Because in a lot of the geodynamic simulations, we do, like, they obviously come off of the sides, but there's still some plumes that seem to rise from the centers. And even in this little schematic, there are plumes in this schematic, at least, that are coming off of the tops of the LLVPs. And so, for example, like I was talking about these ULVZs as possible mantle plume routes, and they may actually occur like within the LLVPs. And so that might be, for example, what's happening at Hawaii. So because Hawaii is kind of not on this map, this is a slightly older map, but Hawaii is kind of like within the margins of the LLVPs. And so it's possible that that's something that's either rooted to a ULVZ or it's coming off of kind of the top of like an upwelling kind of edge.
Yeah, well, the geochemists working on Hawaii seem to model it as that Hawaii is right on the edge of the LLVPs. And you can see differences in the chemistry of the different trends in the volcanoes there.
Yeah, so it depends on what your favorite model is. I would say. So that's like, it's kind of a big issue, right? Like a lot of these questions remain open questions until we can do a better job of modeling where the actual edges of these LLVPs are, and how sharp they are, and how that interplays with the dynamics. And so, for example, this model Spiral, which was published in 2021, has Hawaii really just off of the edge, but GLAD has it kind of within this little nub of the LLVP. So yeah, it kind of depends on your favorite model.
Thanks.
Astronomer working with fuzzy objects is no problem. Galaxies don't have edges either. Any last short questions? Fair, thank you so much. It was fantastic.
Thank you guys. This was really fun. Sorry for going long.
All right. Hey, so glad to meet you. And we'll do the awkward Zoom thing where we just go and it's all over. But we do appreciate the talk and
Yeah, well, yeah, thanks so much. I really appreciate it.
Yeah. Bye.